Hey guys, so I'm starting a new series. I'm going to be calling it Tool of the Week. And basically every week I'm going to pick one really important software engineering tool and I'm going to cover it in this video series. So why is this important? Well, because tools are the cornerstone of software engineering. They're extremely important. I think that they are perhaps the most important concept in software engineering, if not the most important. It's surely up there. So that's why it's important. Now, what we're going to do in this video series is basically we're going to cover the basics or the foundation or the commonly used features of these tools. As you know, software engineering tools can be very complex. They usually are very complex. They have tons of features and they're not always very intuitive or easy to use. So because of those reasons, we're not going to go super in-depth into any one of these tools, but I'm hoping to give you enough level of detail so that you come out being competent in that tool. And then if a certain tool interests you a lot, you can go ahead and dig deeper. I'll give you a solid foundation on which you can build upon. So to start this series out, we're going to cover one of my favorite tools. I really love this tool. It's called Sympy. It's a symbolic math library for Python. So for those of you who don't know what a symbolic math library is, they're also known as a computer algebra system. Maybe you've heard of that. But if you still don't know what that is, basically you can work with expressions. You can work with equations. So for example, you can define an equation like y equals x squared, and then you can tell you can tell Sympy to solve this for x. Rearrange it for x. You can tell Sympy to take the derivative of this expression. You can tell it to take the integral of this expression. You can tell it to plot this expression. So it really lets you master symbolic expressions, which is a little different than what you normally do with programming, right? You work with numbers, usually. You don't really work with symbolic math. So that's exactly what Sympy allows you to do. It allows you to do symbolic math using Python. It's a really amazing software. I really love it. Ever since discovering it, I've been playing around with basically math more. So my math skills as a result of Sympy have leveled up significantly. Anyways, enough talking. I'm going to go ahead and show you what Sympy can do. So to reiterate again, in this series, I cover one important software tool per week. I give you a solid foundation in the tool. I give you the basics, so the commonly used features. But you're not going to come out of here an expert in the tool. If you want to be an expert, you're going to have to do your own subsequent digging around. But you should come out of every video, with a solid foundation in each of these tools. So again, enough talking. Let's go ahead and let me show you what Sympy is all about. Hey guys, welcome to your first episode of Tool of the Week. In this series, we're going to cover one important, one prominent, one useful software engineering tool every week. So let's see what tool we're going to be covering this week. Fancy animation. So this week we're going to be covering Sympy. So Sympy is a symbolic math library for Python. So you can work with expressions and equations. The prereqs for this tutorial, I guess, for this particular video, you need to understand the basics of Python. But that's not really required too much. As long as you've programmed before, especially if you've programmed using another dynamic language, you should be fine. The basics of math helps as well. Things such as, what is an equation, what solving an equation means, and what plotting and graphing an equation means. And we have some optional requirements as well, some more advanced math, or rather intermediate math, such as what derivatives and integrals are, what a linear system of equations are, what matrices and vectors are. This is optional because Sympy lets you work with matrices and vectors. It lets you take derivatives and stuff, and it lets you work with linear systems of equations. If you know what these things are, this tutorial will go a little bit smoother, but this is optional. The basics should do. Another note I want to make, the software that I'll be using to show you the code is called Jupyter Lab. I'm using it with Anaconda. If you don't know what those are, you don't really have to worry much about it. Maybe in the future I'll create a Tool of the Week episode on those. And if I do that, I'll post a link to those videos in the description of this video. And there we go, as a reminder. So check the description of this video for additional videos that I may have on the prereqs. And if I don't have videos, I will link you to other external resources. So here's what we'll cover in this video. We're going to quickly show you how to import and initialize some stuff, such as how to make the plots and the expressions look pretty when you print them to the notebook. We're going to create some symbols. We're going to create some expressions with those symbols. We're going to plot the expressions. I'm going to show you how to plot 2D expressions, how to plot equations in the implicit form, 2D equations in the implicit form, and how to plot 3D plots. I'm going to show you how to substitute things inside symbols in an expression. We're going to talk about immutability. Basically, all objects in Sympy are immutable except matrices. I will reiterate that because it's pretty important. We're going to show you how to solve any equation. We're going to solve a system of linear equations. We're going to differentiate and integrate an expression. We're going to also show you some simplifications. And there's multiple ways to do it. Simplify is the most generic way. You just pass an expression and it will try its best. It has an internal algorithm. It will try its best to simplify it. But there's also specific simplifications that you can do. I'll show you those. We're also going to cover matrices, how to create a basic matrix manually, how to create the standard matrices like identity, zero, etc. automatically. I'm going to show you how to scale matrices, how to invert them, how to create a vector, how to transform the vector, and I'm going to show you that you can put symbols inside matrices and vectors as well. So you can work with symbolic matrices and vectors. Oh, we don't want to go to the summary yet. Okay, so let me show you the code. All right, so the sections here basically map to the basically points that I have over here. So we're going to do each of these one at a time. Okay, so to import and initialize, I usually like to import Sympy as SP. You can import it as whatever you want. And then this second line over here, starting with the percent symbol, that basically means to put the plots that we create inside the notebook. Otherwise, they would pop out in a separate window. The advantage of popping them up in a separate window is that you can interact with them. The advantage of putting them in the actual notebook, so this is called the notebook, is that, well, they're inside the notebook. When you redistribute your notebook, then it will show inside here. They won't pop up in a separate window. This line, this init printing function, will make it so that the expressions print nicely, like in a math looking notation. I'll show you that later. Okay, so to create symbols, we use the symbols function, and you pass it in a list of symbols. So I want to create X, Y, and Z. I separate the symbols by space. You can also use comma. So basically, I'm creating a symbol X, Y, and Z, and I'm calling it X, Y, and Z. You know, you can call them whatever you want. These are just Python variables. And here I'm displaying the symbols. So this display function is a Jupyter Lab function. You pass in what you want to display. So here I pass in X, Y, and Z, and it's just showing you. And notice how they're kind of like in a nice cursive math looking font. It's more obvious with this expression over here. We get that because we called the init printing function. Okay, so we create symbols by calling the symbols function and passing a space separated list of symbols, symbol names. So here we create an expression from our symbols, right? I'm gonna assign the expression to the expr variable. I'm gonna make the expression just be x squared. And then another feature of the Jupyter Lab or Jupyter Notebook is that when you just type the name of a variable, it will basically call display on that variable, so it prints it nicely. So there it is, the expression x squared that we just created. That was an expression of one variable with just x. Now we create an expression of two variables, the non-implicit form. I'll show you the implicit form subsequently. So you can't do y equals x squared. You can't type this in the code because Python uses this as an assignment. So that would assign x squared to the variable y. We want the expression y equals x squared. So it's a little weird, but all you have to do is call the eq function. So called the EQ function. For the first argument, pass the left-hand side of the equation. For the second argument, pass the right-hand side of the equation. And we assign that expression to the expr2 variable. So when we print this expr2 variable, we see that it's y equals x squared. So notice y was passed as the first argument of the EQ function. X squared was passed as the second argument of the EQ function. So here we create a two-variable expression, but in the implicit form. So we just do, remember, an implicit equation is when all of the symbols appears on one side of the equal sign, basically. So y equals x squared is the same thing as y minus x squared equals 0. So here's a very, very important note about Sympy. Expressions are automatically assumed to equal 0 by default. So when we do y minus x squared, think y minus x squared equals 0. That's the expression. That's the true expression. So here it displays it as negative x squared plus y, which is of course the same thing as y minus x squared. And remember, there's an implicit 0 over here. It's equal to 0. All right, so that's how we create an implicit form of the expression. And let's now go ahead and plot them. So to plot an expression, you just call the plot function and pass in your expression. So remember, our expr expression was an expression of one variable. It was just x squared. This will basically pass in x from negative 10 all the way to 10, and then plot the output of the function on the y-axis, right? So this is the f of x axis going up, and this is x. So for x, it puts basically values from negative 10 to 10, and the output of those it plots on the y-axis. So we're just plotting a one variable expression. Let's go ahead, if you have an implicit equation, right? Remember expr3, let's go ahead and look at it again. expr3 is an implicit equation because all the symbols x and y are on the same side of the equation. There's an equals 0 on the right-hand side. So again, the symbols are on the same side of the equation. That's an implicit equation. How do we plot them in Sympy? Well, it's very straightforward. You use the plot implicit as opposed to the plot function. Call the plot implicit function and pass in your implicit equation. And it does the same thing. So it chooses an axis for each one of the variables in your equation. So we have the variables x and y in our implicit equation. It chose this axis as the x and this axis as the y, which works out nicely. We're used to this convention. And then it basically, for the x, it put some values, and basically it put some x and y values that satisfy the implicit equation. There we go, it's plotted. Here I'm going to show you how to do a 3D plot. So here we're using expression 3 not as an implicit function, but as a regular function that has an output. So we're saying that y minus x squared is equal to some output, right? And the output here is on the y-axis. Sorry, not y-axis, this up axis, right? We're going to call it the z-axis because we're in 3D now. One of these axes is the x, the other is the y. And the output is the z. So if we look at expression 3, up here, it's, our output is equal to y minus x squared. We notice that it's just x squared along one axis and it's linear along the other axis, which makes perfect sense if we look at this expression. Because if we keep the y constant, we have our z is equal to negative x squared, which is just a downwards parabola. But if we keep the x constant, then we just have z is equal to y, which is a line. So you kind of see this parabola slanted. Just showing you that this 3D plot is indeed correct. So here I'm going to show you how to substitute for symbols in an expression. Let's see the value of expression 3. Just to remind you, expression 3 is negative x squared plus y equals 0. Remember, that equals 0 is implicitly there. Now we want to substitute for y the value 2. So you do that by calling the subs method of the expression. So the expression.subs, what symbol you want to substitute for and what you want to substitute in. So in y, we want to put 2. And as you can see, inside y, we put 2. Here I show you how to replace a symbol with an actual number. And here I'm going to show you how to replace a symbol with another entire expression. So expression 3 dot subs, we want to substitute for expression 3 for the symbol y, we want to substitute it with basically this entire expression, x to the third. And as you can see, for y, we put in x to the third. It rearranged it a little bit here, as you can see, but it's doing the correct thing. Okay, so we want to talk about immutability here because it's pretty important in the context of Sympy. All Sympy objects are immutable except matrices. So what that means is that any operations, whether you're calling a member function or a free function on these expressions, on Sympy objects, it doesn't modify the original object or expression. It returns a new object or expression, and I'll demonstrate this here. So here we're going to create an expression just 3 times x, and I'm going to print it. Looks like that, thanks to the init printing call. And now I'm going to substitute inside this expression for the symbol x squared. As you can see, x got replaced with x squared in the new expression. And we see that the original expression, when I print it out, is unchanged. So this method, this substitute method, didn't modify the expr expression. It returned a new expression. All operations in Sympy except matrix operations behave this way. That's pretty important to keep in mind. So now I'm going to show you how to solve equations using Sympy. Let's create an expression, 3x plus 6, print it out, there we go. To solve an equation, you just use the solve set function and you pass in your equation. So our equation is 3x plus 6 is equal to 0. What values of x satisfy this equation? Obviously -2. You know, you're going to have to subtract 6 from 6 to get 0, and the only value of x that satisfies that is -2. So here you go. It shows you that -2 is the only value that will satisfy this equation. That's how you solve equations. We're going to get a little bit more complicated and show you how to solve a linear system of equations. So here you kind of have to understand a little bit, you know, linear algebra. You got to know what a linear system of equations are. Otherwise, this may not make sense to you. So if you don't know that, I would suggest maybe looking up on Khan Academy, linear system of equations or something before you follow me with this part. Anyways, so you use solve set, right? You use this solve set function to solve univariate equations, equations of one variable, like we did up here, 3x plus 6. And if you have a linear system of equations, you can have these equations can have as many variables as you want. And in that case, you want to use the linsolve function. The linsolve function is located inside sympy.solvers.solveset module. So this is how you import it. And then we'll go ahead and create 2 equations. Here I'm creating 3x plus 4y equals 6. Note again that if you want to include the equal sign in your equation, you have to use the EQ function. On the left-hand side, as the first argument of the EQ function, put in the left-hand side of your equation, and on the right-hand side, put in the right-hand side of your equation. So it makes sense. Here we're saying 3x plus 4y equals 6. That's what it should create. And then we create another linear function, 5x plus 3y equals 7. So we have 2 linear equations of 2 variables. We know that this system is solvable because we have 2 independent functions. So these are not the same function because you can't just scale one and get the other. And we have 2 variables. This is a solvable system. It's a consistent system. We put both of these equations in a list, and then we pass that list to the linsolve function along with the variables that we want to solve for. So we know we have the x and y variable in here. And now it's going to solve this system of equations. So basically what that means is it's going to find the values of x and y that satisfy both these equations. And it tells us right here that in order to satisfy both of these lines, both of these linear equations, x has to be 10/11 and y has to be 9/11. This is the only point that satisfies this system of linear equations. Okay, I'll make a quick note here and I'll leave it up to you to research additionally, but of course, you can represent a linear system of equations differently. You can put them in an augmented matrix form. Sympy supports that. You can just Google Sympy augmented matrix linear system or something like that. You'll see it in the documentation. And then you can also, of course, represent a linear system of equations as a matrix and a vector. You can solve them that way as well. But I figured the easiest one is, list of equations and pass that list of equations to the linsolve function. That, in my opinion, is the most intuitive. So now let's go over how to differentiate and integrate expressions. So we have an expression 3x squared, right? To differentiate this, so find out the rate that the output of this function, now we gotta interpret this as a function, what the output of this, how the output of this function changes with respect to the x, right? We do expression.differentiate with respect to the x. So you pass in the x as the first argument of the differentiate method. So I feel like I might have said that a little bit too fast. Here we have the function 3x squared, right? We want to find the rate that the output of this function changes with respect to changing the x variable. So the expression is in the expr variable, right? 3x squared. We want to differentiate that, so we call the .diff method, which stands for differentiate. Well, what variable do we want to differentiate the output with respect to the x? Because we may have multiple variables here. And it works with multiple variables as well. So anyways, we see that that gives us 6x, which of course is correct. If you remember how to differentiate functions, you basically multiply the exponent by the coefficient, you get 6, and you subtract 1 from the exponent. So that's 6x, that's correct. Now we have this derivative and we want to integrate it back. Well, it's very similar, it's very simple. Instead of calling the diff method, you call the integrate method, and you still have to tell it what to integrate with respect to. So we want to integrate this 6x expression with respect to x, which should give us back our original expression, 3x squared, because integration is the opposite of differentiation. Now let's talk about simplifying expressions. So first note is that some simplifications, like the obvious ones, are done automatically for you. So let me demonstrate. If we have the expression 3x plus 4x plus 5, right? Clearly these terms, the 3x and the 4x, can be added together. That's done automatically because it's an obvious simplification that most people would want to do. So it results in 7x plus 5. Now, simplification is a subjective thing, right? There's no objective definition of what form of an expression is simpler. It depends on the context. So there's a bunch of more specific simplification functions that you can use. So the most generic one is actually simplify. Simplify it runs an internal heuristic. It's an algorithm internally that it has its own, subjective thoughts of what is simpler, and it will try to do its best. So let me show you that. We have an expression, sine of x squared plus cosine of x squared, right? Well, we know that due to a trig identity that the sine of a value squared plus the cosine of a value squared is equal to 1. If we pass that to the simplify function, it automatically knows that, so it spits out 1. But a lot of the times, the simplify function won't touch your expression because it doesn't really know what's the simplest form of your expression. Because as I mentioned, simplifying something is subjective. So we have specific simplification functions. The expand function basically distributes. So if we have the expression z times x plus y, like that, if we pass it into the expand function, then it will distribute the z. As you can see, it's xz plus yz. If we want to do the opposite of that, we do factor. So when we take this new expression and we factor it, we get our original back. So it factored out the z. And there are more simplifications. You can just Google Sympy simplifications or Sympy rewrite expression and look at the documentation for more examples. And the last thing that we're going to cover is how to deal with matrices in Sympy. So I'll show you how to create a basic matrix manually. You use the matrix constructor and you pass it a list of rows, right? So a list of lists. I like to format my list like this because it kind of looks like a regular matrix, right? But as you can see, it's just a list of lists. Each internal list is a row of the matrix. So here I'm just creating the identity matrix 1, 1. So this will scale the first component by 1 and scale the second component by 1, of course. Here's how you create some standard matrices. There's the I function that can create identity matrix. You just pass it in the size of the identity matrix. Of course, identity matrices have to be square. That's why you only pass in one dimension. Otherwise, you have to specify both dimensions, but identity matrices have to be square. So you just say a 2x2 identity matrix, and there we go. It gives it to you. You can also get a zero matrix, and zero matrices don't have to be square, so you have to specify both of the dimensions. Here we're creating a 2x2 zero matrix by calling the zeros function. Here I'm showing you how to scale a matrix. So we're going to create an identity matrix 2x2, print it out, looks like this. And to scale them, you just multiply it by the number 2. Simple as that. Okay, so to invert matrices, again, we're going to create a identity matrix. We're going to multiply it by 2, and of course, we're going to get this matrix right here. To invert them, you just raise them to the power of -1. So that double, I forget what the name of this character is. Star? I'm just going to call it the star character. So you do the double star character, and then that in Python means to the, right? M to the -1. So if you raise a matrix to the -1, then that's inverting it, which mathematically makes good intuitive sense. And what do we get? We get 1/2, 1/2. And of course, this is correct because the inverse of this matrix, this scaling by 2, is a matrix that scales by 1/2. If you scale by 2 and then you scale by 1/2, that's the same as doing nothing. So this is correct. Okay, so creating column vectors. So remember earlier I said that a matrix takes a list of lists where the internal list is each row. Well, if you pass it just one external list, it assumes that you want a column vector. If you want a row vector, you have to include the external list as well. So like this. If you do it this way, then you're going to get a row vector. I'm used to dealing with column vectors, so I'm going to leave it like this. So here we're going to create a column vector, just 1, 1, with the components 1, 1. We're going to call it V. And now we're going to transform that vector. So, of course, a matrix represents a linear transformation. A vector is a point that you want to transform. If you multiply the matrix by the vector, then you're transforming that vector. So, simple as that. You just use the multiplication operator, the star character, as I keep calling it. You use that, and it will multiply it. Of course, the matrix that scales by, I believe, let's see, M over here scales by 2, 2. If we have the vector 1, 1, and we scale it by 2, 2, it should end up the vector 2, 2. That makes sense. So here I'm just showing you as the last thing that you can put symbols in the matrices. So the matrices and vectors don't have to have just numbers. You can put symbols. So again, I'm going to use the symbols function to define 2 additional symbols, A and B. I'm going to put A and B inside the matrix instead of 1, 1, just like before. And now I'm going to create a column vector, and instead of putting actual numbers inside that column vector, I'm going to put symbols X and Y. So both our matrix and our vector have symbols in them, right? Now I want to do I want to transform this vector. So in other words, I want to do matrix vector multiplication. And there we go. So clearly this is a matrix that scales the first component by A, the second component by B, and we have the vector XY. When we apply that transformation to it, the first component gets scaled by A, and the second component gets scaled by B. So this symbolic matrix vector multiplication worked out correctly. I'm just verifying it. Okay, I should note that I'm going to be posting this notebook, a link to it in the description of the video, so you can actually run it and play around with it and change the code. So let's go back to our slides here. And let's see. This is all the stuff that we covered. Quite a bit of stuff. You should have a pretty solid foundation in Sympy by now. Maybe you need to practice a little though. There we go with the fancy animation. And now a summary of what we just learned. I love doing summaries because it really reinforces what you learned. So Sympy is a Python library for working with symbolic math, right? Not actual raw numbers, but you're working with symbols, what you're used to doing in all your years of math. So we create symbols, and then we create expressions from the symbols, and then we can do mathematical operations on the expressions. so we can solve the expression, right? So find out what values of the variables satisfy the expression. And remember that expressions are implicitly equal to 0. We can rearrange the expressions, we can take the derivative or integral of them, and we can plot them. It also supports matrices, and remember that you can even put symbols inside matrices and vectors. So remember that all Sympy objects are immutable except matrices. And that's the end of this video. So real quick, if you guys have any questions, go ahead and post it as a comment. I'm very good and fast at responding, I think. So if there's any lingering questions or anything that I need to clarify, post the question as a comment and I'll get back to you pretty fast. Also, please post feedback. It really helps me out, because if nobody tells me, if nobody gives me feedback, then I don't know what I should improve on. So some specific ways that you can give me feedback is, did I go too fast? Did I go too slow? Did I not present enough details? Or did I present too much details? And then was I too redundant? So I want to make a simple point about redundancy. I tend to be pretty redundant when I'm communicating, especially when I'm trying to teach something. But I don't think that's always a bad thing, because I don't expect you to listen so carefully to me that you hear every single word and that you understand everything that I say. The important things I will actually reiterate. I will say them twice, maybe 3 times, because I might assume you might have not heard me the first time. And since they're important, I think it's justified to repeat them. So I tend to be a pretty redundant person, but I personally don't think that's such a bad thing. Let me know what you guys think, though. If I keep repeating myself too much, and if you guys let me know that, then I'll probably tone it down a little bit. Also, if this is probably one of the most exciting series that I've created. I really like it because, as I mentioned earlier, tools are at the absolute cornerstone of software engineering. They're extremely important. So if this series interests you, just go ahead and click subscribe, and then also click the bell icon. I'm not really sure where the bell icon is, to be honest, but I know that you have to click it apparently to be notified whenever I upload. So if you want to be, if you want to keep up with videos in this series, just click subscribe and then click the bell icon, and then you should be good. And that's it. Thank you so much for watching, and I hope to see you guys in one of my other videos. Bye-bye.